Hi everyone, welcome to part 2 of our series of understanding series convergence. In the last part, we understood series that we could evaluate. This time, we're going to focus on series that we can't exactly evaluate, but we can imagine them as two different things. So that's exactly what we're going to be doing. So, as stated in part 1, we said that a series is the same thing as the summation of a sequence, right? So, if this proposes the question, can we evaluate a series convergence by using the exact same method that we use to evaluate a sequence's convergence? Well, the answer is yes and no. Because you see, we can't evaluate a series convergence, but we can evaluate a series divergence. And that's what we're going to prove today. So, as stated before, the sequence converges if the limit as n goes to infinity of a sub n is equal to a finite number. This is going to be some finite number L. However, let's say that L is greater than 0. If we took the series as from 1 to infinity of a sub n, and we had the idea that a sub n is equal to L, which is a non-zero positive term, therefore, S is going to be some terms, so on and so forth, plus L plus L plus L. And this is going to go on forever. So what we say is that this is going to approach positive infinity, which means that this series diverges. But if L was 0, then we would get a sub 1 plus a sub 2 plus so on and so forth plus just an infinite string of zeros. So does this mean that this series will converge? Not necessarily. This just means that it could converge or diverge. And you'll see an example of where a series with the limit that approaches 0 will diverge. And we're going to prove that. So let's go ahead and get into some examples here. So we're just going to have these 3 examples that we're dealing with. So we have this series right here, the series going from 1 to infinity of n over n squared plus 1. Now what we're going to do, we're going to take the limit as n goes to infinity of n over n squared plus 1. And if you notice, this is just end behavior of a polynomial function, or division of polynomial functions. So, since n squared has a higher degree than n, and it's on the denominator, this will increase faster than this. So, this limit is just 0. Alright? So, since this limit is 0, this series could either converge or diverge. So, this could converge or diverge. That means that this test is inconclusive. But, let's go ahead and take a look at this one right here. So, we have the series from 1 to infinity of 1 plus 2 over n to the power of n over 3. So, this limit seems a little bit convoluted, right? And I'm just going to go ahead and write it down. But there's an easy way to evaluate this limit. And we're going to use something called the fact, or just a rule with limit definition of E, or the manipulation of the limit definition of E. So, I'm just going to write it down like right here. Yeah. So we have the limit as n goes to infinity. If we have the limit as n goes to infinity of 1 plus a over n to the b times n power, this is going to be equal to e to the a times b. All right, this is what Black Pen, Red Pen, love that guy. You should check his videos out. This is what Black Pen, Red Pen calls the fact, which is also just a manipulation of the limit definition of E. So as you notice here, we have 1 plus 2 over n to the power of n over 3. So we have 2 over n, that means that this 2 is the same as a, and we have n over 3, therefore b is 1/3. So this limit is just equal to e to the 2/3. And if you notice, e to the 2/3 is greater than 0. So therefore, this will diverge by what we call the nth term test, which is what it says up here. Nth term test, which you can also call the test for divergence if you want. So, Now let's go ahead and focus on this special case called the harmonic series, and you'll see why I call this a special case. So, as you can see, this limit is actually really easy to take. You just take the limit as n goes to infinity of 1 over n, and that's just 0. And that's just pretty obvious, because as n becomes increasingly large, this 1 over infinity, this is just going to pretty much be 0. The quantity is going to get so small as the denominator gets bigger and bigger. So, this one is inconclusive, but this is a pretty special case, and you'll see why. So now let's go ahead and focus on the integral test. This is another way we can imagine a series. So let's say we had this function right here, f of x. This is the same thing as a sequence, an infinite sequence, all right? So this is actually a pretty bad graph for this case. I'm going to go ahead and make it a little bit steeper. So there we go. And we have f of x. This is pretty much the same thing as an infinite sequence, but this time it's actually continuous. So basically what this is saying is this series is kind of the same thing. If we threw in a delta x for this series right here, this is effectively the same thing as a Riemann sum or a rectangular approximation of an integral. So if we go ahead and draw in the rectangles that we're approximating, you'll see that if we add up all of these areas, and of course this isn't exactly perfect or what I'm going for here, but if you notice, if we add up all of these areas, then this is pretty much the same thing as this series right here. So if we have the sum of all the areas, this is pretty much equal to the sum from, let's say, 1 to infinity of a sub n. That is pretty much, again, the same thing. Now, if you notice, of course, this is an estimation, so there are some areas of error, as in the ones I'm shading right here, but the summation and the integral, if we evaluate the integral from 1 to infinity, then they're kind of going to behave in the same thing in this case. But that, of course, comes with 3 specific conditions. So the conditions are that f of x must be positive, it must be decreasing, and of course, it must be continuous. These are the 3 conditions that this a sub n needs to fulfill in order for us to be able to use the integral test. So let's go ahead and focus on some examples here. We have some relatively easy examples, but they get into a bigger thing that I'm going to focus on later. So we have the series from 1 to infinity of 1 over n squared. So what we're going to do is we're going to define f of x as 1 over x squared, and we're just going to do that for notation purposes. So if we go ahead and take the integral from 1 to infinity of 1 over x squared dx, this is pretty much going to tell us if the series converges or diverges. Since the integral and the series are going to behave in a similar manner, if the integral becomes a finite value, the series converges. On the contrary, if this integral approaches infinity or negative infinity or something like that, which it won't approach negative infinity, spoiler alert, it'll approach infinity. If it approaches infinity, then this one will diverge, the series will diverge. So let's go ahead and take a look at this this integral will converge or diverge. So we have 1 over x squared dx, all right? This is going to be equal to the antiderivative of 1 over x squared, just based on the reverse power rule, is negative 1 over x evaluated, why did I just write an integral sign there? Oops. Evaluated from 1 to infinity. And I should also clarify, before I do that, for notation purposes, this integral, it's more proper to write a limit as t goes to infinity of from 1 to t of 1 over x squared dx. This is just for proper notation purposes. So this is the same thing as the limit as t goes to infinity of negative 1 over x evaluated from 1 to t. So this is going to be the limit as t goes to infinity of negative 1 over t minus negative 1 over 1. And of course, these negatives cancel, and this limit just becomes 0. Thus, this integral becomes 1. So since 1 is a finite value that's greater than 0, well, I mean, yeah, it has to be greater than 0, then this will converge by the integral test. So that was a pretty easy example. Let's go ahead and move into another pretty easy example, actually. So this is the exact same series we have here. It's the harmonic series, the series from 1 to infinity of 1 over n. So we're going to follow the exact same steps. So f of x is going to be 1 over x, of course. Then we have this series from 1 to infinity of 1 over x dx. Did I say series? I mean integral. The integral from 1 to infinity of 1 over x dx, my bad. This is going to equal the antiderivative of 1 over x is ln x, and I'm just going to quickly write notation here. So the antiderivative is ln x, so this is the limit as t goes to infinity of ln x from 1 to t. And this should also be a t, my bad. So this is going to be ln t minus ln 1. And if you notice, ln t, and I gotta write the limit here, the limit as t goes to infinity, ln infinity is pretty much just infinity. So this is infinity diverges, so the series also diverges by the integral test. So what I'm going to do here is I don't actually have room to write this. So we know that this series converges and this series diverges, so just take some time to process this work here. Okay, cool. So I'm going to go ahead and erase all this work. And then we're going to go ahead and use this to prove something called the p-series test. So the series from 1 to infinity of 1 over n to the p power is going to converge if p is greater than 1, but also diverge if p is less than or equal to 1. And as you just noticed here, this 1 over n squared, it converges, as we proved with the integral test, and this 1 over n, this is the same as 1 over n to the 1. This diverges by the integral test. And we're just going to look at imagine some special cases here. What if n was negative 1? If n was negative 1, then this negative 1 would go on top. So it would just be the series from 1 to infinity of n, which obviously diverges. So this is the p-series test right here. And as you just noticed, the harmonic series, the limit as n goes to infinity of the harmonic series is 0, but as proved with the integral test and also the p-series test technically, 1 over n, the harmonic series, diverges. And there's actually a numerous amount of proofs, which you can just find online actually. There's a numerous amount of proofs that the harmonic series diverges. There's a pretty interesting one that deals with 1/2, and you should check that out. But yeah, with that, that concludes this video, which is part 2 of our series Convergence. And just to recap, we imagined a series as the summation of terms in a sequence, but also a rectangular approximation for a continuous function interval. And with that rectangular approximation, we derived the p-series test, which is an extremely useful shortcut. And we're going to be exploring this shortcut in future parts. But yeah, that concludes part 2. I hope to see you in part 3 and future parts of the series.